Okay, so we have question 5 from the Step 2 2024 paper. This is a question on basically a bunch of just algebra and manipulating variables. Uh, yeah, but the special thing here is we're dealing with integers throughout this whole question, so that changes up a few things, but overall, not too bad. Could be worse things. Anyway, oh yeah, I forgot. If you want to try this question before, this is the full question. Uh, yeah, that's all. So the first part tells us that, oh, they define two functions, saying that the domain is the set of integers, and then they define these two functions. Um, they don't tell us anything about their ranges, but we can sort of infer that, okay, if we're only working with integers here, and these functions are defined like this, then we're only ever going to output another integer, right? Because we're never doing any like sort of division here, and we're never like square rooting, and we don't have any like other special functions, so there's no way we're gonna get like a rational number or an irrational number out of these functions. So these functions are gonna be from the integers to the integers. And then they ask us to show that f1 has the same range as, basically the two functions have the same range. Uh, so you can sort of visualize it as two quadratics. It's a bit different because of the integer restriction on the domain, but a starting point could be just trying to show that they have the same minimum, right? And when you're working with quadratics, to find the minimum, the easiest way to do that is to just complete the square. For simple cases at least, just complete the square, and then you get something like this. Now, what you can notice is that these quadratics are just the same thing, except one is shifted, right? So if they're just the same quadratic and they're shifted, or one is just a horizontal shift of the other, then they're obviously going to have the same range, right? You can just imagine that as like graphically, right? So yeah, hopefully that makes sense. So yeah, first part, not too bad. Yeah, so for the second part, they define a new function g1 with the domain of the integers, and it's another quadratic, so this will also have the range. Uh, the range will also be within the set of integers. And then they want us to show that the ranges f1 and g1 have empty intersection, which means that they never intersect, essentially, right? Yeah, so if we think about what this last part is trying to say, um, if two ranges have an empty intersection, that means that the two functions can never equal each other, right? So that means that the ranges will never equal each other. So if we just replace f1 with a different variable, right, and g1 with a different variable, to like help distinguish between them, then what this last part is saying is that we're trying to prove that they these two functions are never equal to each other, which means that their ranges are never equal to each other, which means that their ranges have an empty intersection, right? Yeah, so oftentimes when you're trying to prove that something never equals another thing, it's it's easier to try and prove it by contradiction, right? So let's suppose that they do intersect, which means that there are values for s and t such that this is true, right? Such that the ranges do intersect, right? Well, if that's true, let's rearrange both sides to get the squares on one side and then just the integers on the other side. When you do that, you have a difference of two squares, right? So you can factorize it like this, and you have two numbers, two integers in this case, that equal 2, right? And that's a pretty simple case to deal with. You just consider all the cases, right? How you can get 2 with a factor of two integers. And this is just going to be a bunch of simultaneous equations, right? Which are pretty simple to solve. So if you consider this as 2 and this is 1, then you get s as this and t as that, which obviously cannot be the case because s and t are integers. And when you do that for the rest of them, you get that none of them can be true, which means that there's no integer values for s and t, so the ranges have an empty intersection. Because again, it contradicts our original assumption that they do intersect. So that is that part done. Another method you could do is that you could argue that the difference of two squares can never equal 2. And in fact, the difference of two squares can never be in the form of 4k plus 2. If you want to do more research on that, you can, but yeah, that's just a fact that I thought I'd give out there. Anyway, for part 3, they gave us two new functions, f2 and g2, and they both have the domain of integers defined by this. And then they ask us to find any integers that lie in the intersection of the ranges of the two functions. So it's basically the same, it's basically the opposite of what they wanted in part 2, right? And the other part, they asked us to prove that there were no integers that intersected in the range. And now they're trying to find basically the integers that lie in the intersection. Okay, so just complete the square on both of them. You get this, then set them equal to each other. Oh, this should be a t there, but that's fine. Yeah, so set the two ranges equal to each other. Do basically the same thing as you did before. You get this equals 5 now. And then just factorize it with difference of two squares. Consider all the cases. And then when you solve all the cases, you get that they all give the same solution, right? Of the same ranges. So all values of s and t give a value of 2. Hence, the only integer that lies in the intersection of the two ranges, in the intersection of the ranges of the two functions is 2. Yeah, so that's part 3 done. Part 4, which is the last part, and typically in step questions, it's going to be the hardest part. It asks us to show that this is greater than or equal to 0 for all real numbers p and q. Well, this looks very similar to p plus q, right? All squared, which we know that is going to be greater than or equal to 0 because it's just a square number. So if we could somehow turn this into a similar form like this, then that would be great, right? The only problem is we have a difference of pq between them, right? So maybe what if instead we just tried to turn this into that? And the way you could do that is to just half this, right? So if you half this, you get something like this. And we have this in here, right? We can just take our half of p squared and half of q squared from there to get this. And they're all square numbers, so they're all going to be greater than or equal to 0 in this case. Something else you could have done is to just complete the square if you wanted to. And that also works. I think there's some other methods, but I can't remember them right now. So yeah, that's that part done. Now, this part is the hard part. They give us two new functions, similar to before, but instead we have cubics, right? And then they want us to find any integers that lie in the intersection of the ranges of the two functions. So it's basically the same as before, or same as part 3, but we have cubics now, which makes things a lot harder because we need to somehow factorize these cubics. So when you set them equal to each other, you could try a bunch of things. One of them could be like to use the difference of two cubes, right? But when you try and do that, you realize that this squared term in the f3 function becomes really hard to deal with because there's no squared term in the g3 function, right? So we need to somehow get rid of this squared term in f3 function, but somehow keep the what's it called? Somehow keep the cube term, so we can continue doing the difference of two cubes. And yeah, it's sort of hard to motivate, but I think it's just like it comes with practice. You can factorize it, the f3 function, into this, right? S minus 1 all cubed to get rid of the 3s squared. So yeah, we're sort of using the binomial expansion here. We take a 3s from here, and then we'll take a minus 1. And if we take a minus 1, then we need to add 1 to compensate for that. So we get this. And the really nice thing is that because we took 3s out of this, that leaves us with 4s, right? And that matches up perfectly with the 4t here. But when you move all the variables onto one side and the integers on the other side, you get this. And using the difference of two cubes formula, you get something like this. So yeah, this is still not in terms of factored terms, right? We still have a plus here, an addition here. So we need to somehow factorize it even more. But what we see is that we have this term, right? S minus t minus 1. And then we also have this term, s minus t. The only difference is a constant, so we can just take out some constants from here. So if we just, in this case, minus 4 on both sides, we can factorize this into 4 multiplied by s minus t minus 1. And then factorize it even more. So you get this. And then you can factorize this term out to get this multiplied by that, which equals minus 11. But if you recall, they made us show that this thing here for all real numbers is greater than or equal to 0. And you can spot this thing here in the difference of two cubes here, which is the same as this term. Yeah, so that gives us that allows us to conclude this, right? Because this term is greater than or equal to 0, which means that this whole term is going to be greater than or equal to 4. So this term can't be negative, which means that this term has to be negative, right? So the only product that it can be is if this term is minus 1, and then this other term is is just 11, to get minus 11, right? And when you set them equal to each other, you get that s equals t. So you can plug s equals t into this term. Solving that, you get two values for s, which is the same value for t. And that gives you, if you plug in those values, s and t back, because they want the intersection of the ranges, right? Yeah, plug s and t back into any of them, any of these functions. You get the two ranges are going to be 10 and minus 11. And yeah, that's the whole question.